Okay, anyway, back to the notes. So today's section is another way of classifying matter. We've talked about classifying matter via its density. We've talked about classifying matter through chemical or physical properties. We've talked about classifying matter as solid, liquid, gas. Here's simply another way, either a pure substance or a mixture.
What page are we on? Page
3.
Page 3 in the top
Page
right
3.
corner.
All right, we did all these. The pure substances, remember, are either elements or compounds. Elements you would recognize easily because they're on the periodic table of the elements. If it's on there, it's an element, it's a pure substance. And they're only made up of one type of matter, like only one type of atom. Gold is made up of gold atoms only. The end. Compounds, on the other hand, are composed of more than one type of matter. So we have more than one type of atom bonded together. But they can be very different than the elements that compose them. So we talked about salt, Na, and Cl. Sodium is a metal, chlorine is a gas, but together NaCl is salt. And that's something I wanted you to think about when we're doing our metal sculptures. Things can have metal atoms in them that don't look like metal at all. All right, so sometimes compounds can look and have properties very different than the elements that make them up. They cannot be easily separated. We can't just run them through filter paper and get the Na separate from the Cl. There's no physical means to separate out compounds. We'd have to set up some sort of chemical reaction, if possible. They have a definite chemical composition. So like salt and water, I can put however much salt I want, however much water I want. There's no set way to make salt water. But water is always 2 H's to 1 O, H2O. So there's always a set composition. And that's one of the biggest clues, is sort of just look for the chemical formula. If there's a sort of a chemical formula you know associated with that thing, it's going to be a compound. Okay, so what are mixtures? Well, it's a mixture. It's what it sounds like. It's a mixture of pure substances. So mixtures are composed of more than one substance which each retains its own identifying property. They can be physically separated, so I don't need to set up a fancy chemical reaction to separate out the components of a mixture. And they don't have a definite composition. Like I said, the salt water. I can use however much salt, however much water, doesn't matter. But the ratios for water, that is a set composition, 2 H's, 1 O. Now, when I say physically separated, here's your list of physical separation techniques, or at least a few of them. Dissolving. Okay. Say you have, I don't know, you found some rock, and you want to separate out certain minerals in the rock. Maybe even salt is in the rock, or some sort of sandstone. Put it in water. The salt should dissolve out, and you'll be left with everything but that. Okay, so that's one way to separate something out. Filtering. Well, that's really separation by particle size. Smaller particles will go through, smaller molecules will go through the filter paper. The larger stuff will be stuck or left on top. Evaporating. Back to the salt water. How could you get the water out and the salt left behind? How could you do it quicker? Meaning?
Heat it up.
Yeah, heat it up, boil it. Okay. Decanting. You ever have a ketchup bottle and there's like a little bit of liquid on top?
Oh, yeah.
It's kind of gross. And you either shake it up to mix it back together, or maybe you just pour off the liquid on the top.
Oh, no, I shake it up.
You don't want to waste it.
That's why I'm ketchup. I'm wasting it.
Yeah. All right. Appreciate you not wasting good ketchup.
Moist up talking. I don't like it.
But if you poured that liquid off the top, that's sort of a fancy, or decanting sort of a fancy name for that. Pouring a liquid off the top. If you have a separation like that, sometimes yogurt you can do that with too.
Oh, yeah, great yogurts. You're all bad about that.
Magnetic separation, we'll use some magnets in the lab today. Anything that's magnetic, you can use a magnet to separate out. Separation by particle size, even just hand picking. And chromatography, which was like what we did with the ink running through the filter paper. Now let me ask you this. Let's say we have blue ink.
Blue.
No, let's say we have green ink. All right, what do we know from our crayon days that green is a combo of what colors?
Oh, yellow and blue. Yellow and blue.
Yellow and blue. Okay. So green is a combo of yellow and blue as far as pigments go and dyes. Not talking about light, because primary colors of light is a whole different story. But we know that green will be made up of blue and yellow. Okay, so let's say you used a green marker and you let this dye spread out through your filter paper, and you see sort of a blue and a yellow line. Which would be a smaller molecule, the one that is farther away from the center or the one that's closer to the center? So let's say you have a distinct blue and a distinct yellow. I'm not sure where they are. But which one's going to be smaller?
The one farther.
Good, the one farther away. It is able to move faster. It's kind of got like less drag. So maybe the blue molecule is longer. So the blue is going to spread out more slowly, and the yellow would spread out a little faster, and that's why you end up with that separation. So that's sort of how the chromatography worked. Similarly, that's sort of how they do DNA testing. They'll run DNA through sort of this gelatin material, and the longer segments will travel more slowly, the shorter segments will travel more quickly, and based off of where you see these little markers, how far these little molecules traveled, you can compare to other people's DNA samples and say, oh, well, this person had a marker here, exactly where this person did. Perhaps they're related because it's very similar.
So they run it through a gelatin?
Yep. I'll see a picture of that in a little bit. Okay, so mixtures can be separated into two types. Just like pure substances could be separated into elements and compounds, mixtures can be separated into homogeneous, or you could say homogeneous, and heterogeneous mixtures. And you should know what these prefixes mean. It's good vocabulary. Homo means same, hetero means different. So a homogeneous mixture is the same throughout, and the components cannot be seen. So it looks like a smooth, evenly consistent mixture. Solutions are homogeneous mixtures, like salt water was one example I kept talking about. They don't always have to be liquids, although we usually think of solutions as liquids. But the components are close to the particle size of individual particles and are too tiny to be seen with a microscope. So just like, little itty bitty H2O molecules and little bitty NaCl molecules mixed up as a solution of salt water, that's homogeneous. That's the same throughout. It's not like one part of your solution's more salty than the other. It should all be evenly spread out. The common food example we use here would be like, homogeneous would be like smooth, vanilla, or chocolate ice cream. Every little bite's going to look the same, taste the same, smell the same. Homogeneous mixture. Rocky Road ice cream, that'd be like a heterogeneous mixture. Not every bite's going to be exactly the same. Maybe you get some chunks of marshmallow in one and not in the other. So heterogeneous mixture is kind of just a random mixture. The components are not evenly distributed throughout, and it's easy to see component parts. Like I can easily pick out the chocolate chunks or the marshmallow chunks. So here's a whole little list of certain types of matter, and I just want to see if we can distinguish them as first, pure or mixture. And then, if it's pure, is it an element or a compound? If it's a mixture, is it heterogeneous or homogeneous? So let's go through them together. What? Yeah, you can abbreviate if you want. All right, and the first one's probably even debatable. Well, this part's not debatable. Ethan, is air pure or a mixture? Is it a pure or a mixture?
Pure.
It's pure? So air is made up of one thing only? It's a mixture. There's lots of things in air, like what? Carbon dioxide, oxygen, nitrogen. Okay, so it's definitely a mixture of all these other pure substances.
You need to write this.
Oh, no. I mean, what I'm about to write, I want you to, I haven't written it yet.
You write compound / homo?
No. It's a mixture. Would you say heterogeneous or homogeneous? Let's see what I said.
Hetero. Oh,
I thought it was homogeneous.
those components cannot be seen in homogeneous.
Right. This is debatable. I would argue that the air in the world as a whole is heterogeneous because, like, how might our air different from the air in LA?
Their air is terrible.
Yeah, their air is probably more polluted. So it's not totally evenly consistent throughout the whole world. But if you wanted to take the air inside of a sealed box where nobody's exhaling in one spot, nobody's breathing, just a sealed box of air, I would argue that that's homogeneous. Still a mixture of things. So perhaps bad to start with a debatable one, but you might even want to write in parentheses like entire world. I will try not to give you a debatable one on the test. All right, soil. I think this one should be pretty straightforward. Taylor, what do you think? Okay, is it pure or mixture? Good. Heterogeneous or homogeneous? Good. Heterogeneous as well. That would totally be a little bit more random. You got some more rocks and gravel in one area than another. Maybe some more worm poop over there. Less over here. All right, Sahil, methane. And I even give you a little chemical formula, CH4. Is methane going to be pure or a mixture? Sahil. Or pure. Now, if it's pure, is it an element or a compound? Compound.
How's it pure?
Because it's just one little...
Methane is just CH4. It's always carbon and 4 hydrogens.
Those aren't
Always.
things.
No, this is methane's formula. So that's kind of a hint. If I give you the chemical formula, that's going to be a compound. Now, how did you know CH4 was 2 separate elements? Maybe we don't. So here's a hint. If you see a different capital letter, that's a different element. Those of you that like to write in all caps, you really can't do that when we're talking about elements. The first letter is always capitalized. If there's a second letter, or even a third letter, it should be lowercase. Some on the bottom. All right, so compound, that's good. All right, Blake, you got milk. Pure or mixture? Mixture, good. And as a mixture, is it heterogeneous or homogeneous?
Homo.
Another debatable one. Another debatable one, but so long as we're not talking about spoiled milk, every sip of milk should hopefully taste the same, smell the same, look the same.
Homo don't mix.
You can't see the components, but they're in there. I mean, you still got... It's the same throughout. Like each sample is the same. Okay. Good question. All right, next one, Keegan. Water. Is it pure or is it a mixture?
Pure.
It's pure. Now, is it an element or a compound? Very good. And I didn't give you the formula, but you should know H2O is associated with water. You should know water is a compound. All right, bromine. Yeah, okay, you might not know this one. Bromine is Br. It's number 35. So if I'm telling you it's up there, is it pure or a mixture?
It's going to be a pure.
And it's going to be an element or compound.
It's going to be element.
There you go. All right, we already did Rocky Road ice cream. That was heterogeneous. Definitely a mixture, kind of random.
Iron.
All right, iron
Element.
is an element. It is up there on the periodic table of the elements, so it must be a pure substance, must be an element.
Homo. It's homo.
All right, this was also the example I used. Vanilla ice cream, assuming it's not the ice cream with little like vanilla bean chunks in it or something.
Compound.
Okay, apparently you guys are on a roll with it.
Element. Mixture. Hetero.
Ink is a mixture because we did that chromatography lab with it. Homogeneous or heterogeneous for ink?
Hetero. Homo. Like
You said homogeneous, you are correct. Because ink, think back to the markers of ink we were using. You know, if you have black ink or green ink, you know, when you write with it, it's always green ink. It always looks the same. We were able to separate it, simply proving it's a mixture. But originally, together, it is a homogeneous mixture. All right, lastly, carbon dioxide. It's made of carbon and oxygen, so that's a compound.
Let's get this lab.
Let's get this lab.
All right, get your lab notebooks out.